Ladies and gentlemen, you may have heard of this technology called RAID. Now, it's not something that most of us will use at home, but we've probably heard of it as, that magical thing that helps commercial servers handle storage. And yeah, it's supposedly very good because, well, hard drive failure becomes a thing of the past. Well, of course, nothing is actually magical in the world of computing. So what we're going to do today is we're going to actually jump in to take a closer look at what RAID actually is and try to understand how it works. You're watching another Random Wednesday episode on 0612 TV. Hello and welcome back to another Random Wednesday episode. So, first of all, what is RAID? RAID stands for a redundant array of independent disks. And in fact, the name itself should tell us something about, how this technology actually works. There are multiple disks that create some kind of redundancy. In fact, to use the proper terminology, RAID is a storage virtualization technology. Its main role is to actually combine multiple storage devices, usually hard drives of the same type and same capacity, into one logical unit. And what that means is basically your operating system, whatever computer it is, sees your RAID array as just one hard drive. That sounds quite simple, but what's really interesting is how it actually combines all these devices together and the smart way in which it does that to both protect your data as well as to give us some other conveniences. The way we actually consider how RAID devices work is by levels. Different RAID levels basically do slightly different things when it comes to how it combines the hard drives together. And what we're going to do is we're going to look at several of the more common levels, starting from what we call RAID 0. RAID 0 is the simplest of all. All you're doing is you're combining multiple drives together to create one large drive. What this means is if we have 4 drives of 250 gigabytes each, using RAID 0, you can create what will appear as a 1 terabyte drive to your operating system. Now, the method that is used by RAID to combine these 4 drives together to, allow them to work in tandem is actually called striping. Here's how striping works. Let's say now you have a chunk of sequential data, let's say we label it as little blocks from A to L, and we want to write that to a RAID 0 volume. Well, the way this works is, sequential blocks of data is actually distributed between the drives. As you can see, this creates a pattern that, sort of mimics stripes, hence the name. So yeah, striping is a technique used by several different RAID levels. Now, in addition to being able to actually use multiple drives as one large drive, RAID can also confer some other advantages. For example, you can have an increase in throughput. What this means is operations like reads and writes on the RAID volume is actually faster than working with a single hard drive. Now, take for example a read. If you were to read some data from a single disk, you would expect the data to basically be streamed block by block. But if we're actually using multiple disks in a RAID volume, what we can actually do is we can read from the drives simultaneously. Each drive has to do less work, but at the end of the day, we get out the same amount of information in less time. Of course, there is one disadvantage, particularly in RAID 0, and that is if any drive actually fails, the whole array is irrecoverably damaged. The reason for this is, of course, well, we can no longer reconstruct the file. Certain areas of the file are lost, and there is no mechanism to actually help you combat this problem. So yeah, that's RAID 0. While it is powerful and has its advantages, this is one major disadvantage, and that's why other RAID levels also exist. At the opposite end of the spectrum, we have RAID 1, which uses a very different approach to actually combining your disks. In fact, RAID 1 uses a method called mirroring, and the idea is the exact same data is stored on the 2 different disks. Now, traditionally, a lot of the time, RAID 1 is done with 2 disks. Of course, that doesn't stop us from, at least theoretically extending the idea to any number of disks. Of course, the great thing about doing things this way is that, well, all you need is one of the drives to remain functional, and well, things will work correctly. Of course, the disadvantage of this is because we are actually maintaining copies of the data, the array will only be as large as the smallest drive, so the storage capacities of all the disks are not added together, unlike RAID 0. Now, very similarly to RAID 0, if you're doing reads, they can be serviced in parallel. So yeah, reading is fast, though writing is actually as slow as writing to just one drive, seeing as that the same information needs to be written to every single drive. Now, there is actually an unofficial version of RAID 1 called RAID 1E, and this actually combines striping with mirroring. So this one looks a little bit more complex. Basically, every piece of data is duplicated at least once, and yeah, subsequent blocks of data get striped. Now, this method is sort of the middle ground between RAID 0 and RAID 1. If any disk fails, that's okay, because, well, you still have a backup somewhere. In fact, in this method, you can even have another disk fail. As long as these two failing disks are not adjacent to each other, that's fine. We can still reconstruct our data, like so. So yeah, even in a very bad case like this, well, we still have a solution. So let's move on again, this time to RAID 2, 3, and 4. Now, the idea of these is that we still want some robustness to problems, to failures, but we don't want to maintain a full backup like we did in RAID 1. So instead, we use error correction techniques, namely parity checks. Now, we've talked about parity before in an earlier video, so I won't go into too much detail. Look for a YouTube card on screen, you can click on it if you like, to go to my earlier error checking video. Of course, I'll quickly summarize the idea here. Basically, there are two parity schemes, odd parity and even parity. For the purposes of simplicity, we'll just look at odd parity. So here's how it works. When you have a stream of bits, what you want to do is to count how many ones there are. In this case, there are 5 of them. This helps us generate the parity bit, because the idea is if there are an odd number of ones, we set the parity bit to 1. So in this case, since there are 5 of them, we go ahead and set it to 1. Now, why is this useful? Let's say now we have a different string of bits, and one of the bits has actually gotten corrupted. Luckily for us, we do actually have our parity bit. Now, since it's 0, we know that there is an even number of ones. We count the ones that we have already received, and we realize that we already have an even number of ones. What this means is, the remaining digit must be 0. If it's 1, we break the parity, so it must be 0. So yeah, that's how you can actually use a parity bit to try and recover missing data. So with this knowledge in mind, let's go back to take a look at our RAID arrays, particularly RAID 3 and RAID 4. The idea is, out of, the bunch of disks, what we do is we store parity information on one of them. So the data gets striped across most of our disks as per normal, but the last disk is used to store parity. Now, RAID 2 is slightly more involved, because instead of using parity, it actually makes use of a Hamming code. Now, I'm not going to go into the specifics of Hamming code, because that's just too much for this video, but yeah, I do go into a lot of details in my error checking video, so do check that out. So anyway, as we've just seen, RAID 2, 3, and 4 all make use of striping, but they actually approach this in a slightly different manner. In RAID 2, we're actually striping the bits. In RAID 3, we're striping bytes, and in RAID 4, we're striping blocks of data. While this might seem like, a very minor detail, this actually causes RAID 2, 3, and 4 to be implemented quite differently. You see, because of the way data is actually striped on RAID 2 and 3, what needs to happen is the arrays have to be physically synchronized. What this means is the spindles on these 3 hard drives are actually spinning together in tandem. One disadvantage of doing things this way is that, well, you no longer get any speedups from parallelism. RAID 4, on the other hand, stores data in blocks. As such, they don't have to be synchronized together, and well, you get the same advantage when it comes to parallel access. Now, here's another disadvantage of RAID 4. If we were to take a look at RAID 0 first, you realize that if we were to write to random blocks on a RAID 0 array, that's very fast because, well, at the end of the day, all you're doing is you're writing, a small number of blocks to a large number of disks. In a technology like RAID 4, this is almost similar, but unfortunately, the need to also update the parity causes a bottleneck. In this case, we're updating the same 3 blocks, but their associated parities also need to be updated, and this is what creates the problem. While writes to the data disk are very quick, writes to the parity disk become sequential, and that is what creates the bottleneck. What happens is that in this example, the first 3 disks remain idle for a very long time, waiting for the parity disk to finish its writing. This problem is solved by RAID 5. Instead of having a dedicated parity disk, well, it actually distributes the parity among all the different disks. So yeah, if we try to actually make the same random writes as earlier on, notice how the act of updating the parity bits is also a distributed operation now. And what this means is, in terms of what is eventually written to the disk, well, it is nice and even. We still have the same kind of robustness against drive failure because, well, when any drive fails, we can still figure out, the contents of the missing drive, either through the already available parity bits or through the generation of a new parity. RAID 6 takes this to the next level. Instead of just computing one parity, we compute a second parity using a slightly different technique. This allows you to account for failures in two drives, any two, even if they are adjacent. The disadvantage of this method is that, well, computing the second parity is much slower. Obviously, this second parity cannot be the same as the first one, otherwise it will not actually provide the additional information needed to recover the data. Because the data is actually striped, concurrent reads can be very fast. So yeah, we've looked at several basic ways of actually combining multiple drives together in a RAID volume, but, well, there's nothing to stop us from actually combining RAID devices together. Let's say now I had 4 disks. Sure, I could do something like RAID 0 and combine them all together, but, well, I could also build smaller RAID drives out of them, and then combining the RAID drives into a larger RAID drive. In fact, what you've seen here is a very popular way of doing things, and it's called RAID 10, or more correctly, pronounced as RAID 10. Essentially, the name comes from the fact that we are doing RAID 1 first, and then we're doing RAID 0 on top of that. Let's look at how this works from the top down. The top RAID 0 array is just going to see, well, 2 disks. Of course, then it makes sense to say that the data is actually striped across the 2 disks. However, if we were to delve deeper, we'll realize that these are actually RAID 1 arrays. And what this means is, well, they contain at least 2 disks with mirrored data across them. So combining 4 disks together in a RAID 10 array actually helps you get some sort of a best of both worlds thing. While you will not be able to get the full storage capacity out of the 4 disks, you do get a fair amount of additional storage, as well as assurance that, well, your data has its backups. This method is robust against failures even on many disks. As long as all the RAID 1 arrays are still functional, well, your volume still works correctly. This method just works well, and its relative simplicity is what makes it such a popular choice. Of course, this is not the only way to combine multiple RAID levels. For example, we have a method called RAID 01. The way this works is we do RAID 0 first, then RAID 1 at the end. So not much difference here, we are doing the same thing in a different order. Since you have RAID 0 at the lower level, the data is being striped across the 2 adjacent disks. But since we're doing RAID 1 at a higher level, well, your second RAID 0 volume actually contains a mirror of this RAID 0 volume. There is RAID 03, that is RAID 0 first and RAID 3 on top, where you have certain RAID volumes holding data and other RAID volumes holding parity. So yeah, there are many different interesting things you can do with RAID, and well, they all sort of give you a trade-off between either giving you more space or more robustness against failure. And there you have it, that is the magic behind RAID. What makes it particularly interesting is of course how it can detect and recover from error conditions. That's all there is for this particular episode. Thank you very much for watching, and until next time, you're watching 0612 TV. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.